Hey everyone, and welcome to The Explainer. Today, we're diving right into the absolute core of our digital world. We're going to demystify that magic inside your devices and look at exactly how computers use zeros and ones. We're stripping away the glowing screens, the slick software, the whole shebang, and getting right down to the fundamental truth of digital computing. It's all about how incredibly simple on and off electrical switches literally power the modern world. Let's get into it.
Okay, here's our roadmap for this explainer. First, base 2, the binary system. Second, counting with 0 and 1. Third, turning numbers into text. And finally, logic gates, computer brain power.
Kicking things off with Section 1, Base 2, the binary system.
You know, this entire explainer really centers around one massive idea, translating human reality into machine reality. And to understand that translation, we kind of have to contrast our world with the computer's world. So we humans operate on the decimal system, right? Base 10. We use 10 digits, 0 through 9, which makes total sense since we evolved with 10 fingers. It's incredibly efficient for us. But computers? Well, they're electronic devices. They rely on circuits that are either energized or not, literally just on or off. Because of that physical reality, digital computers internally use the binary system, or base 2. It literally only uses 2 digits, 0 and 1. And yeah, while long strings of ones and zeros are basically a headache for human eyes to process, they are absolutely perfect for computer electronics.
Now, what's really fascinating here is how these different worlds interact. We're looking at decimal compared to binary, along with a couple of other systems used in computing like octal and hexadecimal. The absolute crucial takeaway here is that all of these number systems are equally capable of representing any quantity. You can take any decimal number we use every day, say 5 or 15, and perfectly convert it between these various systems without losing a single drop of numeric value. No translation lost.
Moving right along to Section 2, counting with 0 and 1.
Okay, so saying they translate perfectly is one thing, but how does the math actually work under the hood? Let's bridge that gap. Think about it. How do we actually translate a standard human decimal number, let's just take the number 9 for example, into computer code? How does a simple 9 become a string of zeros and ones?
Well, there's a brilliantly simple method for this called successive division. Honestly, it's like a fun logical puzzle. Here's how you do it. Step 1, you just divide your decimal number by 2. Step 2, you take the remainder of that division and record it over on the side. Step 3, you take your new quotient and repeat the whole process until the number can't be divided anymore and hit 0. And finally, Step 4, you simply read the bits you've recorded from right to left or bottom to top.
Let's actually walk through the math for our number 9. It's super quick. We start with 9 divided by 2. That gives us 4, with a remainder of 1. That first remainder, that's our least significant bit. Next, take the 4. 4 divided by 2 is 2, remainder 0. Then, 2 divided by 2 is 1, remainder 0. And finally, 1 divided by 2 is 0 with a remainder of 1. That last remainder is our most significant bit. And we stop right there because our quotient is 0.
Now, we just read those remainders backwards, from the last to the first, and boom, we get 1001. It's like a cool party trick. We've successfully translated our first human number. The decimal number 9 is perfectly equivalent to the binary number 1001.
So we know how computers count. Awesome. But here is the big twist, and it's a question that might kind of throw you for a loop. How do zeros and ones become letters? Because the crazy reality is, digital computers only process numeric data. They literally have no idea what an A or a B or a question mark is.
Which brings us to Section 3, turning numbers into text.
Let's solve that mystery. This is where we get to reveal the secret decoder rings that computers use to process human language. Since computers only understand numbers, engineers had to create a translation layer. The most famous one? ASCII, which stands for the American Standard Code for Information Interchange. It's essentially just a standardized table where every single letter, number, and punctuation mark on your keyboard gets assigned a very specific, unique numerical value. And fun fact, ASCII was created all the way back in 1963.
And this right here brilliantly illustrates exactly how it works. When you hit a capital A on your keyboard, your computer doesn't see a letter. It actually sees the decimal number 65, which it immediately turns into binary. A capital B is 66. And notice that lowercase letters are completely different. A lowercase a is 97, running all the way up to Z at 122. Honestly, it's just a giant game of numerical dress-up.
But, you know, ASCII was originally pretty limited, mostly focusing on English characters.
As computing spread, different regions obviously needed their own translation tables. Take India, for example. The Indian Script Code for Information Interchange, or ISCII, developed in 1986, maps out regional Indian scripts, like Devanagari. In this specific system, the first vowel of Hindi is assigned the numeric value of 164.
Now, as computing went truly global, having dozens of different competing regional decoder rings became a total mess. So, engineers developed a newer, vastly larger system called Unicode. And I really want to emphasize this number right here, 256. That is exactly 2 to the power of 8, which is the absolute limit of a single byte of data. To make sure everything stayed backwards compatible, the genius developers of Unicode made sure that the first 256 places of their new massive system perfectly matched the old ASCII values.
But beyond those first 256 spots, wow. Unicode drastically expands the digital alphabet on a global scale. It literally provides a unique number for every single character of pretty much all human languages. This is huge. It means a computer can process English, French, Greek, Hindi, and Korean text all simultaneously in the exact same document simply by using this one massive, universally agreed-upon list of numbers. It's a real game changer.
All right, moving to our final section, Section 4, Logic Gates, Computer Brainpower.
So, we've translated numbers and we've translated text. But this is where we see how zeros and ones do way more than just sit there in memory. They are actually manipulated to help the computer literally think. Logic gates are the elementary building blocks of a digital circuit. Think of them as tiny, incredibly strict bouncers standing at the doors of the computer's processor. They take in inputs, usually 2 of them, evaluate them based on very strict rules of true and false, and then spit out exactly one output. And remember, in binary logic, a 1 is usually considered true and a 0 is considered false.
Let's look at the first bouncer, the AND gate. So the crucial point here is that the AND gate has a really strict rule. It only produces a true output, a 1, if all of its inputs are true. No exceptions. If even a single input is a 0, the output is firmly a 0.
This truth table clearly maps it all out for us. If input A is false, so 0, and input B is false, output is 0. If one is 0 and the other is 1, output is still 0. It is literally only in that final row, where input A is a 1 and input B is a 1, that the gate opens up and gives you a 1.
Now, contrast this with our next bouncer, the OR gate. The OR gate is, well, much more lenient. It produces a true output if at least one of its inputs is true. It doesn't need both. Just a single 1 will do the trick.
Anchoring this to the OR truth table, the absolute only time it gives you a false 0 is when both inputs are absolute zeros. In literally all other scenarios, 0 and 1, 1 and 0, or 1 and 1, the output is a true 1. It operates with this incredibly predictable, steady rhythm of logical inclusion.
Now there's also a NOT gate, which simply flips a 0 to a 1 or a 1 to a 0. But what's truly mind-blowing is what happens when you combine these basic gates into things called NAND and NOR gates. These are known as universal gates. By simply wiring enough of these specific gates together, engineers can generate absolutely any logical operation or mathematical expression in existence. I mean, from simple math to the insanely complex algorithms rendering high-end 3D graphics, it all boils down to millions of these tiny universal logic gates working together in perfect harmony.
And that brings us to the end of our explainer, but hopefully it's just the beginning of your curiosity. We've seen how simple on and off switches represent numbers, how those numbers map onto the text of quite literally every language on Earth, and how tiny electronic logic gates process those numbers to simulate logic. Which leaves us with this final, kind of profound question. If simple zeros and ones can combine through universal gates to create a digital brain capable of almost anything, what actually limits the thoughts a computer can have? Is it just the raw number of physical gates, or is it the imagination of the humans programming them? Thanks so much for joining me on this explainer. Keep exploring and stay focused.